guys, this is Caillou, and today we're going to review AP CSP Unit 2, the Internet. We're going to go through the contents: introducing the Internet, connecting networks, addressing the Internet, rolling with redundancy, transporting packets, web protocols, scalable systems, the Internet protocol side, open protocol development, and the digital vibe. Okay, so before we go anywhere, we gotta know the basic definition. What is Internet? So the Internet is a global system of interconnected computer networks that use the standard Internet protocol sites, for example TCP or IP, to link billions of devices worldwide. This will allow us to exchange data and communicate across a long distance. For example, I'm in Canada and you're in France, and can text each other and do stuff. And the Internet supports many services like the World Wide Web, email, file sharing, online gaming, and streaming, which we'll be covering most of them in today's review. Okay, after we know what is Internet, now we gotta know what makes up Internet. So it's split into 5 parts. So well, there's small parts too, but wires and wireless. So wires in the content of the Internet, wire connections refer to physical cables like the fiber optic cables, telephone lines, some things like that. And they connect devices to the network. And advantage of wired connections are that they're more stable and faster than wireless. But well, you can see the disadvantage is pretty obvious. Is that it is needed to have a physical connection between each other. And now let's talk about wireless. Wireless technology, like radio waves, they transmit data without physical cables, as you can see by the names. And examples will be Wi-Fi, cellular networks like 4G, 5G, and Bluetooth. Wireless connections are more wide, so it's wider in range, but can different in speed. So it could be sometimes slower, sometimes faster. And the next part I'm going to explain is the IP. So IP stands for Internet Protocol. So this is a set of rules governing how data is sent and received over the Internet. So every device connected to the Internet has a unique IP address that identifies it. So it allows data to be routed and to track from devices. Examples would be the IPv4, IPv6, which we'll be introducing later. And next one, TCP, UDP. TCP stands for Transmission Control Protocol, and UDP stands for User Datagram Protocol. In general, TCP and UDP are two types of communication protocols used to send data and internet. The TCP transmission control product makes sure that you have a reliable, ordered and error-checked delivery of data between the devices. It is connection-oriented, meaning that it is establish the connection before data is sent. While UDP, user data protocol, is faster but less reliable protocol compared to TCP. It is connectionless, so the data will be sent out without establishing a connection first. TSL, Transport Layer Security. So this is a protocol that provides secure communication over a network. It makes sure data privacy and integrity by encrypting data being transmitted. Often it uses HTTPS. And the last part would be HTTP and DNS. HTTP stands for Hypertext Transfer Protocol. The protocol uses for transmitting web pages over the internet and defines how messages are formatted and transmitted. It also serves when browsers respond to various commands. So HTTPS is a secure version of HTTP, which I mentioned when explaining TLS. And it uses TLS to encrypt communication between the browser and the server. And DNS stands for Domain Name System, the system that translates human readable domain names like the example www.example.com into IP addresses the computer used to locate each other on the internet. So, for example, if you put the example.com onto the search bar, the computer doesn't read what you type, but instead it reads a IP address that it only computer can read. Now we can go into deeper knowledge, network connections, and type based on coverage. So I split this part into three, three parts. So it's LAN, WAN, and VPN. So this is the three types of network connection types. So the first one, LAN, so it stands for local area network. It covers a small area like home or office and uses EarthNet or Wi-Fi. WAN, wide area network, it covers larger geographic areas and connects multiple LANs, so the one I mentioned before. And and VPN stands for virtual private network. So this one encrypts your internet connection, providing security and privacy by routing your traffic through remote servers. So, for example, if your school doesn't allow you to use TikTok, you can use VPN, and then you'll be on your own internet server kind, and then you'll be able to use TikTok again. Yes. And we can move on to our next step. Network connections type based on coverage. I'm going to explain latency, bitrate, and bandwidth. So let's start with bitrate. So this one is the amount of data transmitted per second over a network, and it's measured in bps, bits per second. And the higher bits rate, meaning it has faster data transmission. And the units could also be kilobits per second, megabits per second, gigabits per second, and all those. And just to give you a more visual example, so if your internet connection has a bitrate of 100 megabits per second, then it can transmit 10 million bits of data every second. And I'm pretty sure you have no idea how much that is, because it's not a lot, to be honest. Because like your games, movies, they're like having so much more data usage than what it can transmit. And we can go to bandwidth. So this is the maximum amount of data that can be transmitted over a network in a only in a given amount of time. So we can think of it as capacity of the network, and it's often confused with speed, but it's more about how much data can flow through. And the units is measured in megabits or gigabits, just like the bit rate. And here's an example if you still don't get it. So if if a network with a bandwidth of 1 gigabit can handle more data than a network with a bandwidth of 100 megabits. And let's move on to latency. So this one is the delay between sending data and receiving a response. It it measures how long it takes for a data packet to travel from source to the destination, and it's measured in milliseconds. So if a website takes 100 milliseconds to load after clicking the link, that's the latency of your connection. Okay, now let's move on to addressing the internet. As I promised a few minutes ago, I will be explaining the IP and the types of like IPv4, IPv6. So the IP is a unique numerical identifier assigned to each device connected to the network that uses the internet protocol for communication. So this allows devices to find and communicate with each other over the internet. And the types of IP addresses, there are IPv4 and IPv6. So the difference would be that IPv4 is a 32-bit address, typically written as four decimal numbers separated by periods. So here you can see 192.168.0.1. So this is an example of IPv4 address. This this address supports around 4.3 billion unique addresses, and because it and as we all know, there are more than 4.3 billion people on Earth now, so that's why IPv6 is created, because there's too much people in IPv4. And now let's get to the IPv4 address hierarchy. So we know that an IPv4 address consists of 32 bits, and we divide them into 4 octets. So, for example, the one I showed you before, 192.168.0.1, we can split it into the following parts. So the first part of the IP address would be the network portion. So this one identifies the network that the device belongs to. So all devices on the same network share the same network portion. So the number of bits allocated to the network portion depends on the IP address class. So it's class A, B, or C. Well, they split the networks into this, or subnetting, which I'll be explaining later. And then we have the host portion. So this one is the last 8 bits specific to the device within that network. So wait, no, my mistake. So this one, the last 8 bits is for IPv6. I'm confused those two. So the IP for IPv4, the host portion is the second part of the IP address. This one identifies the specific device within the network, so it's the same. So each device within the same network has a unique host proportion subnetting. So the network can be divided into smaller subnets in by borrowing bits from the host portion to create a more hierarchical and organized network structure. The subnet mask determines which part of the address belongs to the network and which to the host. So, for example, well, we're not going to go deep into this because it won't be not be covered in this CSP course. So let's just get to our next step. So this one is the IPv6 address and IPv6 address hierarchy. So as I said before, IPv6 was created because IPv4 didn't have enough space for all the users. So now this is 128 bits address written as 8 groups of four hexadecimal digits separated by colons. And after IPv6, I don't think we'll ever have anything more than this, because IPv6 has unlimited number of unique addresses. Well, not unlimited, but about 340 undecillion addresses, which it will blow up the world if we have this much people. So there's no way we'll have anything after this. So I'm not going to go too deep into explaining IPv6 address, because as you can see, this is way so long. But okay, I will. So global root prefix is like the first part before this 3. You can see I marked it down. So it's the first 48 bits. And the subnet identifier is the next 16 bits. So now after explaining the address in the internet, let's go to the next step. Alright, this one is routing with redundancy. So I split this into 5 main parts. So it's the IP packet, which is the main definition we gotta get. So this one is the fundamental units of data that are transmitted over an internet protocol IP network. And let's go next to the packet creation and encapsulation. So this process begins at a source device. So this creates a packet by encapsulating data from the application layer. So example would be an HTTP request into a transport layer protocol, which could be TCP or UDP. And then we get the IP header addition, and this one is the packet encapsulating into an IP packet by adding an IP header which contains important routing information, including the source IP address and the destination IP address. And the second step would be routing decision. So the source device or the first router in the path examines its routing table to determine the best path to the destination IP address. And then we go to packet forwarding. So this one is transmitting the selecting router, and the packet travels across a network medium, so like fiber optics or something like that. And before receiving the packet, the next hop router performs a similar action and will determine where to send the packet next, repeating the process of examining the destination and address, selecting the next router along the path. So it just keeps going like that. And our last step would be delivering to destination. So this is the final step of router and delivery. So the last router will forward the packet to the destination device. So it is the device which is supposed to receive the information, and then decapsulates the packet by removing the IP header to access the original data. So let's talk about redundancy and fault tolerance. We're not going to go too deep into this. I'm just going to simply explain the basics of it because it's not that important, to be honest. So the first redundancy, it is this one refers to the inclusion of extra components of or systems that are not strictly necessary for the system's operation but are designed to take over in case of failure. And the main goal of it is to improve the reliability and availability of the system. And fault tolerance is the ability of the system to continue operating correctly even in the presence of faults or failures. This involves designing systems to withstand and recover from hardware or software malfunctions without significant disruption. Okay, so now let's go to the problems with packets. So this happens when an IP does not handle all the consequences of packets. So like there could be when packets can be corrupted, or a computer might send multiple messages and to some kind of location. The location needs to identify like where do the packets belong to which message, and this can arrive out of order. This can happen especially when two packets are following different paths to the destination. And now we're going to specifically dig into TCP and UDP. Okay, guys, let's start with UDP. So this one is a is named User Datagram Protocol. So it is a connectionless transport layer protocol in the Internet Protocol suite. Unlike TCP, which I'm going to explain later, UDP will provide a simpler and faster way to transmit data over network without establishing a connection or ensuring reliability. And let's look at the UDP header structure. So the UDP header is 8 bytes long and consists of the source port, which is 16 bits, and destination, which is also 16 bits, length 16 bits, and checksum 16 bits. And source port is the port number of the sending applications. Destination port is the port number of the receiving application, and length is the length of the UDP header and data in bytes, obviously. And checksum is 16 bits, used for error checking and header and data. Now let's look at the transport protocol TCP. So TCP stands for Transmission Control Protocol. So it is a connection-oriented transport layer protocol in the Internet Protocol suite. It is designed to provide reliable, ordered, and error-checked delivery of data between applications, and it runs over host communication over an IP network. And let's look at the header structure. So first of all, TCP is typically 20 bytes long and includes source port, which is 16 bits. It is used to it is used to port of the sending applications, and destination 16 bits, the port number of receiving application, sequence number 32 bits. It is the number assigned to each byte of data, and acknowledgement number 32 bits. This one indicates the next expected byte from the sender. And then we have the data offset, which is 4 bits. It is the size of the TCP header, and flags 9 bits. This one control flags. It is for managing the connections, and window size 16 bits specifies the size of the sender's receive window for flow control, and checksum. And this one is 16 bits. It is used for error checking and the header for the header and data. Okay, now let's move into the World Wide Web, which in other words WWW. So the World Wide Web is commonly referred to as a web. It is a system of interlinked hypertext documents and multimedia context accessed via the internet. This enables users to browse and interact with contents through web browsers, utilizing a set of protocols and standards that facilitate communications and data exchange. And we are going to specifically dig into domain name system (DNS) and hypertransfer protocol (HTTP). So the domain name system (DNS) is basically a naming system that translates human readable domain like www.example.com into IP addresses like 19.2.0.2.1, which computers use to identify. And at last we have the Hypertext Transfer Protocol (HTTP). This one is are foundational protocols used for transmitting data over the World Wide Web. I'm going to explain on these two like in next slide. So here we're back on the World Wide Web, and it's still the domain name system and the hypertext transfer protocol. Both of the systems are fundamental components of the internet, and they help build the World Wide Web. And here are the domain and IP addresses of the DNS and UDP header structures. I'm not going to go too deep on this because of the time matter, so let's go on. So scalable systems are systems that are designed to handle increasing loads effectively, and they do it by adjusting resources as demand grows, whether from more users, data, or transactions. This this system could maintain performance and reliability for applications and services. And I'm going to be explaining the internet scalability, simple explanation, and the spectrum of scalability. So first we have the internet scalability. This is the um, ability of the internet and its association systems, how they can handle increasing amounts of traffic and data as users' demand grows. So it's basically the same, but this one handles specifically on the internet. So as more devices connect to the internet, as applications require greater bandwidth and faster response times, scalability becomes a critical factor in maintaining performance, reliability, and user satisfaction. And then we have the web application scalability. This one is referring to the capability of the web application to handle increasing loads, such as user traffic. Yeah, I just repeat it. It's just the same, but this one is focusing on uh, web applications. And then we have the spectrum scalability. This one is referring to the different dimensions and types of scalability that the system into computing and network design can exhibit. And this can help organizations to understand how their applications or infrastructures can grow and adapt to the increasing loads. And at last we have the load testing. So load testing is a type of performance test that evaluates how systems behave under expected and peak load conditions. So the Internet Protocol is commonly known as TCP or IP model. It is a set of communication protocols used for the Internet and similar networks. And now I'm going to go dig deeper into. So the layers of Internet protocols suite is split into application layers, Internet layer, transport layer, link layer. So application layer, this is the most upper layer. It is responsible for providing network services directly to end users' applications and defines protocol for data exchange between applications and different devices. So on the middle, I've listed all the uh, protocols that are in it, and I'm not going to go explain one by one because, as you can see, we are already out of time almost. And next we have the transport transport layer, uh, which is the second layer. This layer manages end-to-end communications and data integrity between devices. This one ensures that the data is transferred reliably and in the correct order. So in this one, there's TCP and UDP. And on the third layer, we have the internet layer. This layer is responsible for routing packets of data from the source to the destination across the multiple networks. So this one is handling the addressing and the routing through the internet. And like IPv6, IPv4, ICMP, this one is the Internet Control Message Protocol. They're all inside the internet layer. And then at last we have the link layer. This one is the network interface layer. This layer deals with the physical transmission of data over various types of networks, so like the Wi-Fi, something like that, and it includes protocols that define how data is formatted for transmission. And here we have the open protocol development. So the open protocol development refers to the process of creating, maintaining communication protocols that are publicly available, standardized, and free for everyone to use. So unlike the other protocols which are controlled by the single company or people, open protocols are developed by communities or internal standards organizations. They play a crucial role in making sure that uh, accessibility across the internet and the other communication networks are open. Yeah. And at last we have the digital divide. So I, I took out the key aspects of this and I'll explain them to you. Well, they're not as deep as you really want, so you might want to go and find some other sources because it's just a small review and we don't have much time left. So the digital divide refers to the gap between individuals, communities, or nations that have access to modern information and communication technologies. So like the internet, computers, and smartphones. And then we can go to our first part, which is access to technology. So the most obvious aspect of the digital divide is the lack of physical access to devices such as computers, smartphones, or um, iPads. This might be because of the economic constraints or geographic isolation, like the rural areas or with limited connectivity. And then we have the quality of access. So even amongst the people who have access, there can be a huge difference in the quality of the access. So, for example, people in like undeserved areas may have slower internet connections, and while you or me are enjoying high-speed internet in the at home, watching movies from the internet and stuff like that. This, well, this is mostly due to the location and stuff like that. And then we have the digital literacy. So another important factor is the ability to effectively use digital technologies. So like many people, like those who are older or have lower levels of education, may struggle with understanding of how to use the internet, computers, or like the electronic devices, even if they have access. And then we have the economic and social impact. Here, they exacerbate existing social and economic inequalities, like those without access to internet are at a disadvantage when it comes to education, healthcare, and government services, and as well as job opportunities. Then we have the geographical disparities. This one is when like the urban areas are more likely to have developed infrastructures for a high-speed internet and advanced technologies. Like outside my house, not like maybe a few kilometers away, just a 5G tower, and and for and for some rural areas there are lack of this service. And at last, we have the global divide. So this digital divide exists within countries, but also between nations. Developed nations generally have higher levels of digital infrastructure and usage, while developing countries often are left behind in terms of internet penetration, access to devices, and digital literacy. And that's it for today. Thank you for watching.